I want to remind you about the logarithm functions. Recall that log base a of y is defined to be the number x such that a to the x is equal to y. In other words, log base a of y is the inverse of the exponential function a to the x. And recall that we called a the base of the exponential function a to the x, so similarly, we call this function log base a. In particular, there are some common bases that we're used to thinking about. Log base 2 of x is the inverse of 2 to the x. Log base 10 of x is the inverse of 10 to the x. And in fact, we are so used to thinking about numbers in base 10 that oftentimes you might see log base 10 of x written as just log x with no base. But be careful because there are certain programming languages where this is not true. But on most calculators, this is the notation and it means base 10. The other base that is going to be extremely important to us, and is actually the one that we are interested in right now, is log base e. And this is so important, we are actually going to give it another name and another notation. So let's go ahead and make a definition. The natural logarithm, which we denote by ln of x, is the inverse of the exponential function e to the x. And this function log x is actually going to play a pretty major role in helping us finish computing the rest of the derivatives of functions we haven't been able to compute yet. Let's go ahead and graph the natural logarithm. To do this, we're going to use the fact that we know the graph of the exponential function e to the x. Remember that the graph of e to the x looks like this. It is concave up and goes through the point 0, 1. To find the graph of log x, we're simply going to reflect this graph across the line y equals x, and we get that the graph of log x goes through the point 1, 0, and looks like so. Notice that both log x and e to the x are growing to infinity, but log x grows much more slowly than e to the x because this graph is actually going to be concave down, but it's still approaching infinity. And the other thing that I want to point out is that the slope of the tangent line to e to the x through the point 0, 1, this has slope equal to 1. That's actually how we define the number e. And this tells us that the tangent line to log x through the point 1, 0 is also going to have slope 1. Before we get any further into finding the derivative of this function, I want to remind you of some of the properties of the natural logarithm. And these properties actually hold for all logarithms with any base. And all of these properties follow from the inverse relationship with the exponential functions. These properties are that log a1 times a2 is equal to log of a1 plus log of a2. And this follows from the property that e to the b1 times e to the b2 is equal to e to the b1 plus b2. The other important property is that log of a to the n is equal to n times log a, and this follows from the property that e to the b all to the power n is equal to e to the b times n. I'm going to leave it to you to verify why these properties hold. Before we do calculus with the natural logarithm, I want you to do some exercises to refamiliarize yourself with the log and its behavior.